it did. There we go. And let me do custom show. Nope, that's not it. Setup. There we go. Okay, so this again is a set of slides from 2022 CASMA Colloquium. Some of you were there. I'll go somewhat quick through these.
Did you start recording again?
I did. Thank you for asking. Yes. So if all goes well, it should be recording. So this was the beginning of where this class came from. I named it, I was trying to go with something funny, Tales from Alternate Dimension Customs and Practices in Multidimensional Assessment Models. So I was like, what's a funny title? I'm like, oh, sci-fi, like dimensionality. Like, who else talks about dimensionality, right? It's usually sci-fi, at least. I'm not a big science fiction fan, so I of course, I grew up with Star Wars, but after that, I'm sort of like, I'm not so sure. But, there we go. This is it. Multidimensionality, feature or bug. That's where this all started. Is it a good thing? Our data's multidimensionality. Is it a bad thing? And we'll start off with a little bit of a lot of this is going to come up again next week, so I'll go a little bit quickly through it to jump into Argon. So yeah, we'll talk a little bit about generalized latent variable models. The big distinction is measurement versus structural. Again, that's not a distinction that you hear a lot about in unidimensional IRT, but it shows up in every other measurement paradigm on the planet. Is multidimensionality good or bad? Can multidimensionality be good? My guess is if you're enrolled in this class, you're probably thinking that that's my take. I do believe that we should get more information out of tests. That's where multidimensionality comes from. But then not all tests are multidimensional, so that's part of the problem. So some definitions here. I will use the word score to give us a numeric representation of behavior. That's if you look into axiomatic measurement. I don't know if you've ever heard of that field before. Sort of the philosophy that goes from what is it that we're actually quantifying from behavior and how do we do so. So in our case, the behavior is usually taking assessment items. And it's supposed to be knowledge, like an ability if we're thinking educational measurement. Sometimes we call those latent traits, latent constructs, latent variables, ability or abilities, skills, dimensions, or attributes, depending on which area you're in. It's a lot of jargon, and actually you'll see that as we get into the comparisons of multidimensional IRT versus diagnostic models. The language is very different across each. But that's not to say that the models themselves aren't highly similar. In fact, it's somewhat of a small difference to switch. There's a lot of nuance, but like the conceptual understanding is not that much different. An assessment is a collection of tasks used to quantify scores. An item is an assessment task. A person, student, examiner, respondent is someone giving you data, bless you. And the psychometric models and methods are the linkage between a person's data and their score, their latent trait itself, right? So far, so good. By the way, if you have questions, just stop me. This is going to be a very quick overview.
So it was
Yeah.
axiomatic what?
Axiomatic measurement. It was the sort of the foundational, this was a series of like, the part of psychometrics it resides in the time was like 1960s almost. So sort of what does it mean to measure things? And sort of that idea that if certain axioms are true, then we can arrive at a rank ordering of people that would represent some type of continuum of a score itself. So it's a very technical, very heavy on the logic side, but it was a nice exercise to think about. If you sit back and think, we're all PhD students or have PhDs. The idea is with the PhD philosophy part of it, it's very much the philosophical side of what we do when we measure somebody, right? Like we're observing behavior, and somehow we're going to translate somebody clicking buttons on the computer screen into this rank ordering of students or something like that, right? And how do we go from one to the other? So it's a very deeply philosophical set of papers I wouldn't share them with you because they would pretty much probably put you to sleep, at least if you're like me. But anyway, too much. All right. You'll see this again next week. I'll go more in depth into the models next week, just again for the language. But the theory I like to go with is this, and I mean this because there are whole classes of models that we talked about in item response theory, and they sort of get put into the side, like a generalized, like a nominal response model is this, or whatever. But the general picture is this. We have data, and that data we like to purport comes from some type of property of the person themselves, right? So whether or not we're looking at data as being somebody got an item correct or incorrect, the reason why they were get an item correct is because we think there's some type of psychological dimension or attribute that enabled them to understand and mark the correct answer. Now that same idea could be, instead of data being correct or incorrect, that data could have just been which option they chose in a multiple choice question. The same thing applies. Now, if they pick the correct option, there's something about their status that makes them pick that, right? So what I'm trying to posit to you is that you're going to hear a bunch of names of models, but generally this is the functional form that you see. We have a theory about the trait, and that theory is saying why the trait leads to this type of data. That data, though, shows up in different forms. It's categorical, it's continuous, it's discrete, it's multinomial, right? All the terms about variables and statistics happen to be there. But it doesn't matter what type of data there are, that doesn't affect the theory side, the right-hand side of the equation, right? So you often see that with the path diagram, right? We have a trait that's in a circle for some reason. Circle plus square equals triangle. The old man, that's what I used to always say. When someone shows me a path diagram, look at my model. I'm like, what, am I supposed to add circles? Like, no, not a model. But that's me, sorry. I was on a plane, and there's, I watch my own things on the plane, but someone's next to me was watching, what's that Tom Hanks movie where he's like an old grumpy guy that came out this year?
Oh.
Otto or something like that?
Yeah. A man called Otto.
Yeah, it seemed like I had a lot in common with that guy. That's what I'm going with. Now, I don't know the whole story, because it looked like it was a little emotional and stuff like that. I don't want to get into that.
Look, his face sounds really good.
Okay. Well, I'm grumpy is where I'm going. My son's been playing a video game called Plants vs. Zombies lately. I don't know if you've heard of that. And they have a guy there called Grumpy Stumpy. Sorry, now I have to do it. I have to do this because this is me also. That's him. There we go. It's a tree stump that's all angry. Yeah, that's me. That's that guy. Anyway, sorry. I'm saying that because I'm like, circle plus square. I'll hear myself being grumpy. But going back to trait, same thing. The arrow is supposed to indicate the path of like causality, if you will. Right? The trait is causing the data. Now, we don't have causality. We're not in a causal setup. But we can envision that it's the case that the trait came before the data because we are assessing students, right? They have to have the attribute we're trying to assess, and so therefore, or they have some quantity of some level of the attribute we're trying to assess. Does that make sense? Okay. So small sidebar, you'll hear more about this next time. When you're working in this field, particularly in multidimensional measurement models, when you set up a design, when you set up a study, when you set up an assessment, think of it as what it would look like if you could observe the trait. Right? What do I mean by that? Right? So what's a model look like if we have, let's take a diagnostic model. So students are either high performing or low performing, relatively high performing, relatively low, they want to call it mastery versus non-mastery. We had this conversation. That's like categorical data, right? So we could dummy code or reference code at zeros and ones, right? So what does a model look like if we're doing that? Well, now we've got like almost like analysis of variance mapping onto if it's correct or incorrect responses. It's like analysis of variance with a logit model. Ta-da. Why I say that is a lot of what we do in the models map onto really classical designs. So for instance, I had done a lot of psychometrics with diagnostic models in my history. I had one study, one result, it was actually a paper with Lisa, where I had a result that seemed a little weird. There were eight classes of 8 different types of people. And several of those had very close to 0 people in it. And it sort of suggested that we were overfitting the data, but it was like, well, how are we doing it in what way? And so now it became, okay, when we looked at which classes the people there, it really looked like there was what we would call like a learning progression. First you had to learn this, like facet number 1, if you want to call it that, point number 1. Anybody who hadn't learned point number 1 couldn't learn point number 2. And anybody who didn't learn point number 2 couldn't learn point number 3. So if you think about it that way, now I've got data, but the data have like holes in it. Well, it turns out what the model would look like for that is a nested factor analysis, not factor analysis, nested analysis variance, linear model with nested factors, right? And that led to a paper called the hierarchical diagnostic model, which came out after that. So when you think about the tie of measurement and statistics, like it's really, really tied together in a way that you don't necessarily realize as you're learning it, because we teach them in such separate silos. But the more that you force yourself to think about that, better it comes from. So I put some up here. DCMs are ANOVA, CFA is like multiple regression, IRT is like logistic regression, all those types of ideas. Same thing goes when you get in more complicated designs, more complicated assessments. Like the understanding of the design first and what you're trying to measure should always predate doing the assessment itself, understanding the analysis of it. Any questions? All right, so on the data side, if we think of this dichotomy, traits lead to data. On the data side, we have item responses. They can be many different types. Correct, incorrect, like multi-category, like a graded response, 0, 1, 2, partial credit, whatever you want to call those. An integer that represents some score off a rubric. There's all sorts of. Have any of you worked with count data before? How many cigarettes have you smoked this week? It happens to show up on a lot of like healthcare surveys, those types of things. Continuous responses like slider bars or response time, reaction time. All these types of pieces of data, each of those needs a different type of distribution to model it. Right? Those of you in Bayes' class remember that. We had to pick a distribution that mapped onto the data. But none of that changes the theory. It's just the way we collect data about the theory. Right? So it's sort of separate. And so I like to denote Y with PI to represent a response to an item by a person, but this can be any type of distribution right now in the way we're looking at this. There we go. Side note, why use Y when many psychometric texts use X? So if you look at a lot of text, it's X equals whatever for the equation. I like Y because if you think of what we're doing, I don't have the model written out here, but Y we often use in statistics for a dependent variable, right? And it actually takes the form of a dependent variable in a measurement model, because on the left-hand side is the data, and the right-hand side is our quote-unquote independent or predictor variable. So I use Y in that case, because Y looks like a dependent variable, just to remind ourselves we're doing that. In other parts of the world, other parts of science, particularly some psych departments where they don't have a lot of quantitative people, if the department doesn't, I've worked there a couple places, they think of factor scores or other things as being like sums of variables somehow, right? Or like principal components almost. And it sort of emphasizes that no, really the factor itself isn't, it's like we have a design, we just didn't collect that piece of data, right? All right, it's already 1:40. Are you bored yet? Let me speed this up. Want to go home, just be like pretend it. The final this year will just be come in and tell me how your life is going.
That'd be great.
What'd you learn in multidimensionality? I don't know, but life is great. The model side looks like this. Looks like a regression in a lot of cases, although in some measurement models it won't look like that. There's usually a tie to some of them to look like this, though. The thetas themselves are the latent variables, but they're really just placeholders. they are, not every item will measure every dimension. Let's also put it that way, right? So that's why that shows up. Then the coefficients, like if this were a regression model, the betas, those would be the item parameters or measurement model parameters. In educational measurement, we usually call them item parameters. Other places, I just call them parameters themselves. But we have an intercept, and these would be, now here's the fun part. Remember in Bayes, I tried to like satisfy everybody. It's a slope, it's a factor loading, it's an item discrimination. We're going to track on another one. It's a main effect in a diagnostic model. But those are all synonyms. They all mean the same thing, right? If you can look at the equation and you interpret this like you would interpret a linear regression, right, where that beta I1 is the change in something for every 1 unit that theta goes up. That's the interpretation that flows through everything, right? The same interpretations that you would use in linear regression. Right? In this case, now that's controlling for the other variables. This is multiple regression. It's really what it looks like up here. All right, so I've talked about the data side. I've talked about the theory side. Let's put them together. That's where the generalized model comes in. When you look at these data from a generalized point of view, the idea is that we are modeling some type of function of the data, usually a function of the mean, with our psychometric model. So what do I mean by that? Like here, right, in a factor analysis, this is the equation. An item response, y for a person item, is equal to some intercept plus some, in this case, factor loading or slope times the latent variable theta, plus a residual variance e. This is, if we had observed theta, this would be a simple linear regression, a single predictor, a single outcome for one variable. If you think about what that really means is we are modeling the mean of y with this equation. That's what the translation is. Even though it doesn't look like it, it really is. If you take in a class from Lisa Hoffman, she'll talk about the model for the means, the model for the variances. Remember that? Those of you who have. The model for the means is everything except for this error term. And that actually is what we're saying, conditional on a person's theta, that we expect their mean to be this linear combination of mu plus theta times lambda. Right? And so one way we denote that sometimes is just saying that's the expected value of y conditional on theta. You don't, when you're working, if everything was linear regression or everything was factor analysis in this case, you wouldn't really think about modeling the mean, but that's really what we're doing. If we think about the data being binary, the same thing happens, right? On the right-hand side, we may have mu plus lambda times theta, or if we reorganize it slightly, we'd get our traditional unidimensional IRT form, A times the quantity theta minus B. But what that's doing is actually modeling the probability of a correct response. If you have binary data, the probability of a correct response is the mean. So yet again, our psychometric model is modeling the mean of the data. Yeah.
But isn't it also modeling the variance?
Yes. Well, in the Bernoulli distribution, the mean is the probability. The variance is the probability times 1 minus the probability. So when you model the mean, yes, you are implying a very specific variance as well too. But the point I'm trying to make is why the theory doesn't change when the data do is that generally speaking, in a generalized linear model framework, in this case, generalized linear latent variable framework, sometimes called the GLAM, I kid you not, of psychometrics, generalized linear latent and multi-level models.
Or is it additive?
What's that?
Not additive.
Let me find out. There's a book, 2004, by Andrew Schrondel and Sophia Rabba Hesketh. It was generalized latent variable modeling. But they talk about that. GLAM. I think it's Blam.org. Anyway, generalized, linear, latent, and mixed models. So it's a big umbrella term for everything thrown together. Why I say that to you, again, is you think about our program. We have a class for factor analysis. Now, when Lisa teaches it, you also get IRT there. And you get some of the count. Do you get the count models in her class there? I think a few of them, right? So you get different types of data. We have a class for IRT, which is generally binary and multinomial data, right? Multi-category data. Just putting it all together is important. It's all under the same umbrella. That's where this is going. All right. The other thing I will note, as you're probably familiar with, but this is an upper level class. Remember, there's a lot of frameworks, a lot of equations look like this over here, where there's an intercept and a slope. Sometimes we call that slope-intercept form. In the one instance, like this shows up for every model, but like 2 or 3. Right? And one of those 2 or 3 takes up 99% of the rest. That's the binary IRT models. This other format, A times theta minus B, where A is often called the discrimination parameter and B is often called the difficulty parameter, we often call this notation discrimination difficulty. But you can see one's algebraically there, we can use some algebra and get from one to the other. Right? So just because it may be specified in one way doesn't mean it's always the same case. In particular, if you think about it, when we have more than one theta, what does A times the quantity theta minus B do? What do we do with it?
Summing to 0.
No. No sum to 0 on that one. No, it's where do we put theta, right? How do we do it? It doesn't, there's no place for it. So often in the multidimensional models, you will not see discrimination difficulty. You will see a slope-intercept type form of almost everything we do. There's just no place for theta. Okay, questions? You've heard all this from me before, mostly. Some of it. Is it good remember? Good refresher? I don't know. Now I'm asking you leading questions. You really like me? I'm just kidding. Just kidding. All right, so what's in the model? The model is the psychometric mathematical representation. There's data on one side, people on the other. Here are various forms. Here's a CFA model. Here's an IRT model. And here's a couple of multidimensional models, the CFA version and the IRT version. Right? Look very similar. And we already talked about that. So let's get into it. Is multidimensionality a good thing? What do you think? Who thinks it's a good thing? Better yet, who doesn't believe in false dichotomies? Why does everything have to be good or evil, right? No. Who knows? It's a good question. It's surprising to me because this is the part that, I came out of grad school studying DCMs, and so the world I lived in was everything's multidimensionality because we want that. And then I'd talk to someone like Mark Ricase, and it would be like, no, we don't want multidimensionality. We're trying to get rid of it. Right? That's the problem. And it's like, how can we both be in the same field and have that juxtaposition? That is the fundamental question. I want to ask you that, right? I think it probably, where I'm at is it depends on your design of your assessment, right? Multidimensionality is good if you want it to be good, if you wanted an assessment to measure multiple things. It's not so good if you're not measuring multiple things, right? It becomes a nuisance then. But we have to think about it as from that lens, right? If we want it there, we have to do certain things to establish that it's there and to show that it's meaningfully present. If we don't want it there, we have to see how much harm we're doing otherwise. Or we have to go and put statistical controls into a model to sort of limit its damage. That's the main part. So I have this hypothesis, I have this conjecture where this came from. I may be wrong about it, probably am. I've done a lot of homework on it, but here's my rough history of it. Our notions of multidimensionality come from psychology, largely, I believe. Early psychology. So like Spearman, the Spearman, that guy. Had a few influential papers, particularly in 1904. What a great year, right? And that Spearman's approach was to think that there was one general intelligence. Thurstone, another very prominent psychometrician. Spearman was more statistician. I don't even know if we had the word psychometrics back then. But Thurstone comes along and says, wait, we have more than one type of intelligence. We have specific abilities of some sort. And from what I understand, there was a little bit of a disagreement between the two. But if you think about it, that sort of shaped the idea. And then we get into, like, Thurstone's work involved building methods to check for multiple dimensions. So now we have the technology to check for multiple dimensions. That sounds good. So guess what happened? In other parts of psychology, like in particular personality theory, you start to see crazy numbers of dimensions being theorized. There was Ray Cattell's 16 PF, 16 dimensions. Why not, right? The Big Five, you may have heard of that. Anybody ever taken a vocational interest survey? You know, like there was this very long-running theory called Holland theory that talks about vocational interest. I think Holland has ties to ACT as well too. Maybe you might know a little bit about this as well. There's 6 different dimensions there, right? So when you think of it from the psych point of view, like something like openness to experience or neuroticism, something like a personality characteristic, we often don't think of those as changing very frequently, right? And so that, to me, is where we get most of our notions of what a multidimensional model is. We have a set of things about a person that are fairly stable that we try to measure. Now contrast that with education, right? In education, oftentimes our assessments are unidimensional. There's math, or there's reading of some sort, right? Science. But they're built on unidimensional. I mean, they're unidimensional scores, but they're built on multidimensional constructs like standards, right? And so, if you have an assessment, let's say you're giving out my son's in 3rd grade, so 3rd grade math assessment, and you give him a 3rd grade math score, but each of the items measures one or more standards of 3rd grade mathematics, right? Is that a unidimensional assessment? Is that a multidimensional assessment? Who knows? But beyond that, the nature of the trait is changing. Because when you assess the child, right, they will either be in the middle of learning it, or have learned it, or have yet to learn it, right? And think about that. That's like saying how would the psych theory change if we were assessing like the Big Five and then actively intervening? Like we measured someone's neuroticism, and then we actively intervened to change it. Like, what do you think that would do with whole like dimensionality thought, right? Because we're aggressively trying to change it. Another thought experiment for you. My son likes math. He will horribly fail a calculus exam, right? As will most of the 3rd grade class, I would guess. I know we're in a university town, so I'm going to put it out there that maybe some 3rd graders are derivatives, but not everyone, right? So if all of them fail, the amount of variation is shrunken in our scores. It's very difficult to find dimensions, right? Similarly, flip the script a little bit. If we all took the 3rd grade assessment in here, I'm guessing we're all probably going to pass, right? I saw some of the standards, you know. Yeah, there may be some variation.
It's the new math.
The new math.
The new math.
I know I'm past break, but let me get this comment out and I'll get done. Like, we would also look unidimensional is where I'm going with that. But if we took that exam and we gave it to him when he was trying to learn 3rd grade math, I believe that will not look unidimensional, right? And so that idea of dimensionality that we use often in a measurement sort of forgets that we're actively intervening to change the dimensionality of the students. That's one way of putting it. I mean, that may be too strong of a way. We're actively intervening on the traits. As a secondary effect, that might change the dimensionality, but we don't think about it that way. We don't look at it that way, and that's what I want you to think about as we do it. I'm past the time for a break, so let's take till about 5 minutes after 2 and come back. Does that sound good? All right, let me pause the video here. Stop it.